这个 the string liquid is formed by the equal superposition of all string configuration. That's what we discussed in the last lecture. So now we consider a different wave function. Remember that we have a two-wave function. One is the equal with the superposition of all strings, all loops. Another is with plus minus sign. So then we emphasize that these two wave functions cannot be distinguished by their ground state degeneracy. They're always the same. But however, they belong to two different topological orders. So basically, we try to show that these two wave functions, they are not connected by the local unitaries. So this is just a. So we have this this Lagrange entanglement state is equal to superposition. This one is a superposition with plus minus sign. We want to show that these two wave functions cannot be connected by this local unitary transformation. Yeah. But how to show that? One way to show that is just try to construct and try to show there's no finite depth circuit that can connect the two. And but this is too hard. So I try to using a more physical way to show they are not connected, but it's not rigorous. So the physical way is again we want to determine what is the property of an string. You know, for this wave function with plus minus sign, then it also have an string. Okay. But however, the and string would have a different fractional angular momentum. The reason is the following. You can see that again we try to do a 2-pi rotation. After 2-pi rotation, the straight one go into the hooked one. Okay. And then, but this right hook and the left hook are related. But the relation changed. Because right hook and left hook differ by a string reconnection. But now the string reconnection have a minus sign. So therefore, the right hook is a minus the left hook because under fluctuation, the wave function have this kind of amplitude. There's a sign. And then we make another 2-pi rotation. This one becomes straight one. So therefore, this 300 2-pi rotation have this kind of matrix element. It's minus 1, 1 minus 1. Yeah. So straight became hooked, and the hook became minus straight. You know, there's an actual minus sign. And now this matrix have two eigenvalue plus I minus I, no longer plus 1 minus 1. The eigenvalue are different. So therefore, we have the straight plus I hooked is eigenvalue I. It have a spin a quarter. And straight the minus I hooked have a spin minus a quarter. Okay. And then this quarter spin means Sammian, means it's not fermion, not boson, but something in between. So we call the Sammian. Okay. And so actually, this term is invented by Tony Z. And because when we study this, we say, oh, there's some statistics between boson fermion. It's not 0, not pi, but pi over 2. Then I say, okay, let's give this a name. We call it Sammian. I thought, okay, yeah, that's fine. Call it Sammian, it's okay. And but it's I think it's a pretty good name. So I think it's the people kind of accept this and use it pretty commonly, you know. So sometimes introducing a good term, a convenient term, is pretty important. And so therefore. So therefore, we have this Sammian. Again, this S plus and S minus, these two Sammian only differ by a sign here, you can see. So therefore, from S plus to S minus, they differ by this the vortex. Vortex is that if we have a mark place, every loop going around it give us actual sign. The wave function would have an actual sign if you have an actual loop around this marked point. And then the difference between these two states is that from straight to hooked is like adding a loop. But the adding loop here is plus I, adding loop here is a minus I. That means S minus have extra vortex, have actual cross there. That is so therefore we can view that the S plus when you combine with M, this vortex give us S minus. You can view that way, yeah. So that's give us some fusion rule. Okay, and I think no, I didn't write down the fusion rule for Samian. So this kind of topology order is called the double Samian topology order, because it still have a four type of excitation. They have a S plus, S minus. Their bound state we call M, and then the trivial one. So if you include the trivial excitation, it have four type: 3 non-trivial type, 1 trivial type. And this kind of topology order have low energy effect theory. It's a mutual Chern-Simons theory. So I just mentioned this mutual Chern-Simons theory. I won't discuss it. So that's again one of a so-called topological quantum field theory. The Z2 gate theory is also a topological quantum field theory. The mutual Chern-Simons theory is also a topological quantum field theory. So that's kind of a fancier name. So this may be actually very general. The low energy effect theory of a topological order is always a topological quantum field theory. Actually, that's the reason why we call this topological order. Because their low energy effect theory is topological quantum field theory, and that's why we call it topological order. Yeah, that's another the motivation for the name. Okay, so now clearly that these two string wave function have a different property. In one case, the string end is a boson fermion. Another case, a string end can be Samian. This plus I Samian or minus I Samian. These two different Samians. So therefore, these two string liquid are really different topology order. They are not connected by local unitary. They do not belong to same phase. Okay, so this is physics is the way to show that these two particular wave functions are not connected by quantum circuit. Using quantum, I hope someone in the quantum information can show that directly, but we don't know how to show that directly. So we go a detour, go a long way around. We by study their string end, their property of a string end, and their different statistics. And then we show that these two really belong to different phase. They are not connected by local unitary. Okay. And there's some reference that this the Z2 topology order was, I think, first studied in 1901 by Nick Reed and Shachdev and myself in two different papers. And in both papers, one is using slave boson theory, another using slave fermion theory. At that time, people using slave particle theory to construct spin liquid. So both the slave boson theory and slave fermion theory gave rise to this Z2 topology order. But however, the slave particle theory is, it's only believed by believers. So that time when people study high-density superconductor, there are so many schools, and the different school believe different things, like different religions, and so the one believe slave particle theory would believe these results. The one don't believe slave particle theory do not believe these results. So it's not very clear. Do we really have a spin charge separation? Do we really have this emergent anion, emergent Samian, emergent Fermi statistics, emergent Z2 gate theory, all those kind of emergent things from a quantum spin system? Is this possible? And it looks like it's a trick of slave particle rather than a physical property of a system. So it's so it's very hard to convince people. I write many papers on slave particle, but the referee always asks me to write, despite the hundreds of papers published, none of them are shown rigorously by any numerical calculation, by any controlled calculation, the conclusion is correct. They're all conjecture. But things changed in this 2001. This Emerson and Sondy did some quantum Monte Carlo calculation on a triangular lattice. So this is this numerical calculation confirmed this slave particle results. So people start to believe, yeah, maybe this Z2 gate theory from quantum spin liquid indeed can appear. But however, even before that, the Kitev have this Topological model. But that time, this result is not widely known within condensed matter. The Kitev's Topological model is written, I think, in 1997, but it's not widely known. And actually, the Topological model also support this Z2 topological order can emerge from this quantum spin liquid. And this double Samian topological order actually is studied later. So the Michael Friedman and they have a large group of people. They study some mathematical some homology of loops, and then Michael Levine and I studied the string net, and which both produce this double Samian topology order. Okay, so now let's consider something even more general. So again, kind of like a cartoon. So later we'll go into this more concrete mathematical formulation and calculation. And here the motivation is that we want to consider more general topology order. You can see we consider loop liquid. And in 2 dimensions, the loop liquid can be, one of the loop liquid can be the equal weight superposition. Then another loop liquid can be with a superposition with a plus minus sign. And here we will consider more general liquid, which we call the string net liquid. So here we allow a string to branch. Remember, the string just downspins, the string of downspins. And here the rule is that the downspin cannot have AND. In this case, we still have same rule. The downspin form a string which cannot have AND. But however, 3 string can join. So we allow this branching point, this 3 string can join. So in this case, they form a network. A single string cannot have AND, but a 3 string can join. Then we have a superposition of this kind of string net. That's also a partial sum of all possible of the string of the spin configuration. And this partial sum also gave us a highly entangled states, also gave us a topology order. So we consider this one. And but however, the dancing rule is more complicated. Okay, so the so-called dancing rule really describing ground state wave function. So this ground state wave function have a property that if we continuously deform a string, the wave function don't change. But however, the reconnection is complicated. Remember before, if you only have loops, the 2 strings can reconnect. The reconnection usually gives us a plus sign, minus sign. But here reconnection is complicated. So the idea is the following. So now let's look at this. So this shaded area means some other string configuration we didn't specify. So the shaded area is just some arbitrary other string configuration. So in the middle, we have a we have a string, we have a loop, we have string this way and string this way. So basically, this really that we have this region. This region have a 4 incoming string. In this region is disk. There's a 4 string going into this region. When the 4 string go into the region, they can be connected in different way. For example, when the 4 string, for this 1, 2, 3, 4, 4 string go into this white disk, they may be internally maybe connected this way, or they may also be connected this way, or they may be connected this way or that way. There's a different way for 4 string going to this to be connected. Okay, so that's one point. So now let's say, what is the reconnection rule is following? The wave function with a string in this configuration are related to the wave function with a string in these two configuration. Okay, so basically the idea is here is that when the 4 string comes into this region, we may connect 4 string like this. These 2 string connect, this connect. But however, because we allow stringnet, there may be extra string in the middle. So therefore, this is one possibility. So this is one possibility. So basically the string internal structure on the disk may be this or maybe that. But however, we can also view a string in the other way. That is the wave function can also, so this is like a horizontal channel, and this is like a vertical channel. So what we try to express here is that we express the 2 possible states in the horizontal channel by the 2 possible in the vertical channel. So at the moment, it's just an arbitrary rule. We just try to express the wave function are connected. So the amplitude of stringnet wave function are not independent. The different string configuration have different amplitude, but their amplitude are related. And that's it. So we just say they have different related amplitude. So this is the generalization of the string rule before. Okay, you can see that in the previous reconnection rule, again we have a 4 string going to this area, but this one is like a horizontal channel. This is a vertical channel. Again, we try to express horizontal channel in terms of a vertical channel, using that to express some relation of a string wave function. Here we have 2 states in horizontal channel, 2 states in vertical channel. Then we just using their relation to express the wave function, try to describe a dancing rule. Okay. But because we have two horizontal channel, 2 vertical channel, then their relation would be like a 2x2 matrix. They have 4 coefficients A, B, C, D. Okay. So you can view that this A, B, C, D just data to specify ground state wave function or to specify how string dance. You say why this is reasonable? Because the change of string configuration are always local. So this kind of dancing rule can be implemented by the local Hamiltonian. So why this is reasonable? So this is a local relation, local dancing rule. So we do this relation. But then there's an issue is that this A, B, C, D is should have some relation. So what is their relation? Okay. So now let's consider how to get a relation of A, B, C, D. And so first relation is the called unitary relation. So ABC is 2x2 matrix, actually it's a unitary matrix. Okay, so how to explain this unitary matrix is the following. Let me try to explain this unitary matrix. So let's look at the horizontal channel. So actually these 2 graphs can be viewed as following. we can view this straight line is a link of lattice. So this is a link of lattice, this is another link of lattice. This is the third link and the fourth link. There's 4 links of lattice. But we also have a link in the middle. So from here to here, there's another link. That's on the link. And on each link, we have a spin. Spin up or spin down. If a spin on the link is up, we mean that link have no string, because up spin means no string. So here we view that, remember, we view string live on the link of a lattice. If a spin live on the link of a lattice, if a spin is up, there's no string. So spin string is very close. So if a spin is up, there's no string. If a spin is down, then there is a string occupy that link. So therefore, this picture means that here we have a string. That means on this link, we have a down spin. On this link, we have a down spin. Here we have down spin, here we have down spin. But on this horizontal link, we have up spin. Up spin means no string. So basically, then on the same lattice, the middle part, this link have a down spin now. So that's why I have 2 states, because the incoming link is like external. This middle horizontal one is the internal. The internal one, spin can be up or down. If spins up means no string, spin down means have a string. So basically that's what we describe here. So this the spin up means no string, spin down we have 1 string. We have 2 states. This horizontal channel is this vertical channel is similar, but we have different lattice. This external leg is the same. We have this 1, 2, 3, 4. This external one still have external 4 links. But the internal link now become vertical. So this vertical link have a up spin, and here the vertical link have a down spin. And here we did something very unusual. We related 2 wave functions living on different lattice. You can see actually this graph here have different lattice. And usually we don't do that in kinematic physics. Usually we have a same lattice, we have a wave function on the same lattice. And here we did something more than that. We have on the right-hand equation, we have a wave function on one lattice. On the left-hand side, we have wave function on another lattice, and we compare these 2 wave functions. Why this is illegal? And then I just want to say the 2 things. Usually, compare wave function on different lattice is illegal. We should not do that. But somehow this is convenient. Means that we want to find a relation wave function on the same lattice. We do not want to evolve a new lattice. But somehow to express relation wave function on the same lattice is complicated. So we introduce a new lattice as a helper. We say the wave function on this lattice are related to wave function on the new lattice. But the new lattice wave function, new lattice also related to wave function on the old lattice. Then through the new lattice, we obtain relation wave function of the same lattice. So this is the one way to understand why we do this. We introduce new lattice just for convenience, so that the wave function on different lattices are related, which induce wave function, relation wave function on the same lattice. So just a good direction describe wave function from here to here is hard. It's easier to go from here to a new lattice than from new lattice to back to old lattice, and this is easier. So this is one way we do this. Another thing is is more fundamental. Actually, another is more fundamental. Is that let me just say this. So here on this local graph, we have 5 links. So this is 1 link, 2 links, 3 links, 4 links, and the 5th link is the horizontal one. So in this little graph, we describe 5 spin and 5 links. And these 5 links are configured in certain ways. 1 link here, 1 link here, another 2 link here, and there's a horizontal one. But on this side, again, we have a 5 link and 5 speed, but they're different. The 2 link here, 2 link here, then the link in the middle. But somehow, the total Hilbert space is the same, 2 to the 5th. But however, we organize this 2 to the 5th Hilbert space, 5 spin, differently. And in particular, the middle one are different. So you hope you can see what I'm talking about. It's again hard to explain. But this is like a quantum gravity, basically. It's that link. The lattice is like the fabric of space-time. It's a lattice. We usually view a lattice as a background. But here, we're describing 2 lattices as different choice of bases. And this may be the keywords. And we have Hilbert space of 5 spin, a 2 to the 5th dimension Hilbert space. That is a 32-dimensional vector space. And there's one tensor product decomposition. We can decompose the 32-dimensional vector space into 5 tensor product of 5 2-dimensional vector space. But there are 2 different tensor product decomposition. One tensor product decomposition gives us this kind of configuration. Another gives us this configuration. So therefore, in this point of view, the 2 different lattices is same lattice, just 2 different point of view, different choice of basis. So I myself find this point of view is a very stimulating. It's that the different lattice actually is like a choice of basis. So that really sounds like a quantum gravity. The space-time dynamics and the different choice of basis and the different lattice, different metric, somehow they seems all connected. So I think I'm not going to talk about the quantum gravity here, but in this point of view, there's some flavor of quantum gravity embedded into this. That even a different choice of lattice is like a different choice of basis. I think this is the key words here. And so we really consider the decomposition for this 32-dimensional Hilbert space into the 5 tensor product. But the 2 decomposition is really related by the different choice of orthogonal bases are related by the unit transformation. So this is why we assume this A, B, C, D form a unit 2x2 matrix. So they start with this relation. So this relation really means that this A, B, C, D is a 2x2 unitary matrix. Okay. Again, there's there's no logic, there's no duration, just a guess. And what do I say? You just keep guessing. As long as your guess is consistent at the end, everything fits, then that's fine. And this is kind of more powerful because you can jump a lot, but at the end, if everything fits, no contradiction, then it's okay. Sometimes when you guess, maybe you find a contradiction, then you have to make a different guess, So here is this one reasoning to say, yeah, this is like different choice of basis, so we have unitary transformation. Okay, then the most important thing is the self-consistency. That's just a moment. The self-consistency is that remember this kind of reconnection move. We say if you do it twice, it's go back. So therefore, this phase can only be plus minus 1. And so therefore, we cannot put arbitrary complex number here. Similarly, we also have a self-consistent here. We have A, B, C, D here. But there is some self-consistent relation. So A, B, C, D cannot be arbitrary. Not only A, B, C, D should satisfy this condition, there's some other condition to satisfy. Yeah. So I will explain that in a moment. Yeah, please. Okay, so what is a self-consistent rule? Okay, and so I'm doing this first thing. So we have this configuration is A times something and B times something. but something is written as a further decomposition. It's a falling. And so here I just I think I make a 90-degree rotation. So here we say we express horizontal channel to vertical channel. But if you rotate yourself by 90 degrees, you can view those vertical channel as a horizontal channel and apply this rule again. Okay, and so basically what I did here, and so then when you view this vertical channel as a horizontal channel and apply the rule again, you go back to horizontal channel. But rotate by yourself by 90 degrees and apply that rule again. Okay, and so this is convenient. So we get this. So now everything is horizontal. Okay. So therefore, the ABCD should satisfy this condition. So when you're collecting terms like these, now you're just collecting terms together, you can show that they should satisfy this condition. And this condition is not very strong actually. We still have a squared plus b squared equal to 1. B equal to c is something, and d equal to minus a. But we still cannot determine the ABCD altogether. There's something, we determine something, but we cannot fix them completely. But this rule is simple, so I describe this rule first. You just very naturally rotate the 190 degree, apply this rule again, you know. So this is a failed attempt. You know, we try to derive some self-consistency condition, hoping to fix ABCD completely, but we didn't. We did not fix ABCD completely. Okay, and so this is a real thing. And so actually, there's a more systematic generalization to generalize to obtain the self-consistent dancing rule. Rather than you rotate yourself by 90 degrees, there's something better. Okay. So this something better is to draw things differently. So here again, this part is still this the middle part I described. There's still this middle part. But look at this middle part, the basic structure, middle part have 4 incoming strings. So 1, 2, 3, 4. There's a 4 external one, but the middle they link differently. So the rule here again, same thing. We have a 4 external one. This is a I, J, K, L is a 4 external one. Ignore the arrow. So here our string have no arrow, so you just ignore the arrow. And but in the middle they connect differently. Okay, but here I do things more formally. We say that the string have a label. The I, J, K are label of string. If a label is 0, means no string. If label is 1, means we have a string. So I just draw. I always draw the string. But if a label is 0, means there's actually no string there. If a label is 1, means I have string. Now naturally, label can be 2. If a label is 0, 1, 2, that's more general. We have a no string, the type 1 string, and a type 2 string. And here we do something very simple. We just have a no string and a string. There's a string do not have different type, but this can be generalized. So what I describe here can be generalized even further. Okay, but the reconnection from horizontal to vertical reconnection really go from here. This J go from to the left, from J go to the right. So this the relation we describe here, you know, like this relation can be more generally viewed as just a redraw this J from here to here. That's it. And the picture before what I draw is the following 4 pairs. I assume I, J, K, L all equal to 1, means we have 4 incoming string. But however, if ijkl equals 1, but this m, the middle part can be 0, means no string connecting the two, or m equals 1 means there is a string connecting the two. So these two configurations just m equals 0 or 1. And then another topology, the j go to here. Again, ijkl equal to 1, so there are 4 strings here. But n can be 0 or 1, depending whether there's string in the middle or no string in the middle. Okay. So therefore, this graph and this graph are related. So this graph are labeled, the ijkl is fixed. Only m can change. So m have a range of value. And these different m are related to different n here. So this 2 by 2 matrix is this one. So m can be 0 or 1, n can be 0 or 1, we get 2 by 2 matrix. And so this 2 by 2 matrix is written as this one. ijkl again is fixed. So this m, n are the index 2 by 2 matrix. Yeah. And so this is a so-called F symbol. It's a rank 6 tensor if you include the external index. But the external index are fixed, only m, n are kind of summed over. Yeah. So therefore, this A, B, C, D are encoded in this Fijk, Mn, in this rank 6 tensor. It's A, B, C are encoded here. Okay. And so this is a way to, more systematic way to describe this reconnection, the string reconnection move. I just draw things differently. So like this ij is like you can say that, let's look at this picture like let me see what I described. Yeah, like this. So this is ij, ij is here. And the k is here, l is here. It just rotate differently. Yeah. So in this picture is easy to draw just a j from here to here. So it's easy to see this move. But previously I draw things like this. The label is I here, no, this I here, j here, k here, l here. And this one is m. Now this part is a vertical channel. Again, it's I, j, k, l, and this one is n. Yeah. So that is so just draw differently. Yeah. And so now let's try to expand this. And so it can be ijk all equal to ij if ijk equal to 0. So ijkl equal to 0 means the dotted dashed line. Then m can only be 0. Because if m equal to 1, that would be open string, and it's forbidden. So therefore, if ijkl equals 0, then this is this graph. The dashed line means 0. Then other side, ijk equals 0, the n has to be 0. So this vertical also has to be 0. Then the no string and no string, their wave function relation just they're always same. So this is naturally 1. Yeah. And similarly, like this 0, 0, ij is 0, but the kl is 1. So ij, this I here is 0, j is 0, k is 1, l is 1. Then the middle m has to be 0. And so then on the other side is this ij equals 0, k is 1, l equals to 1, n equal to 1 here. And now these two strings only change by a deformation. So we know the string deformation is 1. So this f has to be equal to 1. So this, although I write down a lot of tensor, and many of them are fixed. Only those tensors, this f110, 110 is A, 110, 111 is B, and etc. So this new formulation for Fijkl and ABC are really only the non-trivial relation is only here. You really have to draw a lot of things, and to really see this. But all other things just a string deformation. So all this case, the string have same connection, just deformed differently, and so that's why they all equal to 1. Okay. And in this formulation, things are very simple. We can derive this most general self-consistent relation. So this is something I just want to ignore. If everything is real, we can just overlook it. And let me see. This is a complex conjugate. I think it's really. I think I use unitary relation here. I'm trying to see. I did not give rise to the complete story. So what I try to say is that this matrix, this 2x2 matrix is a unitary matrix, and this unitary matrix gave us some relation between F symbols. So I use that to, I use that relation and here I think. Yeah, sometimes this F and F star are related because it's a unitary relation. I think that's a thing I used here. Yeah. The full relation is a little bit more complicated, and there's a complex conjugation rule. It's to enforce unitarity relation. Yeah. For the real, we can ignore this part. That's a part of the reason why I assume everything's real. I think the most important thing is this one, is to get the self-consistent relation, we should consider this kind of graph. This more general graph. Now here we have five external leg, I, J, K, L, and the P. The bottom one is the P. I, J, K, L, P. Okay. And then we can deform a string differently. So we want to deform this graph to this graph. Okay. But it can through two different ways. One way is that we can move this K from the left to right. So here we shift the K. Then we shift the J. Now from here we shift the J. So through two moves, we go from here to here. So that's one way to go from one graph to another graph. But for each move, we have some kind of transformation. Oh, I should drop this index here. This simplification, I don't have index. So this beta chi should be dropped. So for each move, we have F symbol. And so we have two moves, we have two F symbol. So we really have to apply this move together. Okay. And then in here, we do things in different order. We first move J leg first. We move J attached to K. Then here we have intermediate state is T. Then we move this T attaching to L. Then to here. Then we move this K attached to L. So in the second case, we take 3 F moves to go from here to here. So first case, we go 2 steps. In the second case, we go 3 steps. But both have the same end. It's like from A to B. There's 2 ways to go from A to B. But these 2 ways to go from A to B should produce the same results. So this gives us a relation. This 2F together and 3F together should be the same because they are the same relation between these two graphs. And this is the most general relation. Yeah. So this is the more general description. But in more details, let's look at the first one. So when we move from J attaching to the I to J attached to K, then the internal state here is M, but new internal state is T. So therefore, we have this F symbol is that really internal, this is the M and T are sum, but I, J, K, N are, this I, J, K, N is fixed. I, J, K, N is fixed, but M is dynamical and T is dynamical, so T is a sum here. But I, J, K, N is the same, other things are the same. So that's why we get this symbol. So the more carefully, there's so many indexes here, but the many indexes are just fixed. And some indexes are summed over. So you have to really look at this very carefully. And but in the whole graph, and you can see some indexes are summed, some indexes are totally fixed. And so at the end, but at the end we get a relation between this from here to here and from to here to here. You can see this S Q sum is the same, but the T sum is different. So in both cases we have a QS sum, and so we draw the QS sum, but the T sum is has to be kept. So that's why with the 3F symbol with the T sum should give us a 2F symbol with no sum, because this SQ sum is lifted. Because it can be lifted because they are the basis. Those are orthogonal bases of states. So all the coefficients should be the same. In order for the two bases are related, and all the coefficients have to be the same, because we view this graph as the orthogonal basis. So that's why we get this relation. But anyway, and this is a very, very important. So this is called the Pentagon identity. And so that the 3F symbol and 2F symbol are related. And this is a very general relation of this string net dance. You can see that the string net have a dancing rule, but this describes a string net dance. And then you may wonder why describe this such a complicated relation. Because this is a category theory. So if you don't know category theory, say, oh, this is category theory. Because this actually in the category called the fusion category theory, there's a central relation in fusion category is this Pentagon identity. Yeah, and a different solution of this nonlinear equation gave us different fusion category. So there's one way to study fusion category theory by just study this equation and the solution of this nonlinear equation. So studying this is one way to study fusion category. And but somehow in a string net wave function, this fusion category theory just appear in this way. Okay. So so to obtain a consistent string net wave function, we should solve this. For every solution of this equation, give us a string net wave function. And then we already mentioned that this equation actually already appeared before in the fusion category theory. And in there, the solution is viewed as a different fusion category. So therefore, in a more formal language, that for every fusion category, we obtain a string net wave function. So string net wave function and the fusion category have one-to-one correspondence. So this is a more general mathematical statement that the different string net wave function and the fusion category have very close relation. The reason is really through this Pentagon equation. Yeah. There's some details, but in general, roughly, it's this picture. So let's try to solve it. Okay. This is pretty tough. so there's many labels. Each label have two variables, two possibilities, 0 and 1. So therefore, there's 500 nonlinear equations. If you really counting those labels, to ask how many equations do we have? Here they say 1. This is one line, but because many indexes are fixed, so they have choice. So for all different choice index, you get actually many equations. So in the even simplest case, this I'm describing simplest case. Simplest case, there's nothing simpler than this, except this loop, this Z2 topological order, they are simpler. But beyond that, this is simplest case. And this one have 500 equation, and 64 unknown. And they are nonlinear equation. If 500 linear equation is easy, but the 500 nonlinear equation with 64 unknown. And then what you say there's no solution, because number of equations is much more than number of unknown. So there's should not be any solution. But magically, this equation always have solutions. And so because many of the equations are degenerate, they are not independent. So and also, I think maybe there's really 64 independent equation and 64 unknown. So the solutions are unique, or maybe isolated. There's no free parameter. After solving the equation, there's no free parameter. Yeah. So something pretty magical here. That's I don't know why, because this is people in category theory show this as quite amazing results. Okay, so how to solve this? No, I don't know. And so I write this. You can write Mathematica, using Mathematica to list them, but the Mathematica have a way to reduce equation. You know, we have many equations. They can reduce the equation to some canonical one. It's called I forgot some name, Gabon based some. I forgot that's the words. There's some mathematicians way to reduce equations, and I actually try to do this, but it's pretty difficult. But one way to do this for us is to just pick something. Okay, so here I just do this. I pick this I, J, K, L, P equal to 1. So all this external line equal to 1. Okay. Then we just plug in, T can be 0, 1, but all I, J, K, L, P equal to 1. So we get this relation. But still there's an NMT and SQ. That's still very complicated. Then I take NQS equal to 1, M equal to 0. Okay. Don't ask me why, just do it. And then we get this equation. Okay. We get this equation. This equation, first we have a 1, 1, 0, 1, 1, T. But T can be 0, 1. So we have a 1, 1, 0, 1, 1, 0. Okay, what is 1, 1, 0, 1, 1, 0? Okay, we'll go back to this. Where's 1, 1, 0? Okay, 1, 1, 0, 1, 1, 0 is A. Okay, so here's A there. The reason I choose this index is we want to get ABC. If you choose some other index, it's easy to land here. Its identity is something trivial. And for that choice, I get ABC. So we get A. So we get A. Okay. So if T equal to 0, we get A here. Okay. And T equal to 0, we get 1, 0, 1, 1, 1, 1. So 1, 0, 1, 1, 1, 1. What is 1, 0, 1, 1, 1, 1? So like look at 1, 0, 1, 1, 1, 1, where it is. Here. 1, 0, 1, 1, 1. So that's equal to 1. Okay, so I think we really need a computer to do it. So we get a 1 here. Now here we have a 1, 1, 0, 1, 1. I'll go back to check it. So 1, 0, 1, 1, 1, 1. Oh, 1, 1, 0, 1, 1. 1, 1, 0, 1, 1 is B. Okay. Okay, so then we get the first time is A times 1 times B. Then next T equal to 1. So we had a 1, 1, 0, 1, 1, 1. So that's also B, I think. And then this we have 1, 1, 1, 1, 1, which is minus A, it has a BDU and this. So basically you just plug in, So after all this thing, for this choice, actually, we get this equation. Actually, we get this equation. Okay, but there's a b here, so we can just drop the b. Actually, b equals 0 will be another solution, but the b equals 0 solution is somehow illegal, so we have to rule out by some other reason. And so assuming b is non-zero, then we get this a squared plus a equal to 1. So a have this solution is a plus minus square root of 5 minus 1. But since a squared plus b is equal to 1, so that means only 1 is it will assume everything is real, so only 1 is legal. So it's a equals square root of 5 minus 1 over 2. Yeah. So this is so finally we find a. By the way, once we get a, then using this relation, a squared plus b equal to 1. If you know a, you know b, and then we know everything else. So if you find the one, the others a, b, c can all be found. Okay. So this is the way to find this solution. And so therefore the string net dancing rule is this one. The gamma is this. Gamma is a, basically. It's a square root of 5 minus 1 over 2. That's a gamma. So this is string net dancing rule. Yeah, and we get this string net dancing rule here. So what is the topological excitation? And the topological excitation is that let's assume we have a sphere. Then we have a string end. The end string is topological excitation. Then we ask how many locally indistinguishable states on the sphere. So here is some guess. Maybe we have a 4. Means so this is square representing a sphere, actually, not a torus. This square just means a sphere. So we can have these red dots are 4 on the string. We can connect this way, connect this way, but we can also, because the string net, so we can also add the string here, add the string here. Roughly looks like there's 4 sectors. But you know that this kind of thinking is too rough. It should not be trusted, because string can fluctuate. They can fluctuate in this way. So this configuration can become superposition of these two, and etc. So therefore, we don't know whether it's how many. So how many is a tricky question. So we have to include this redundancy. So how to figure out how many states when we include this redundancy? Okay. So, but why we studied this? Because we want to answer the question: what is the internal degree freedom for the end string? Remember, we asked this question before. For the end string, we find there's only one state. So therefore, there is no string end have no internal degree freedom. But in this case, the answer is actually trickier. When you fix the string end, we have degeneracies. But this degeneracy means that the string end have internal degree freedom. So before we figure out whether this string end is a boson, fermion, or anion, we want to know whether they have internal degree freedom or not. So that's the question. It turns out that for this case, I won't really explain this, but I just explain the answer. So there is a way to figure out how many degree freedom are there. And the way to do that is to have this canonical figure. So we have a four string end. But the first one have this string all the way down. And all others just join the first one in this particular way. So we say this is a canonical configuration. We just counting a state using this canonical configuration. Certainly, why we do that? Because of the following. If we have a configuration like this, which is string going in different direction, we can using this f moves to move from here to deform this to this. Actually, we can deform every configuration to this form. So this is like a canonical one. So every other one can be deformed into this one. But deform into that one really means using unity transformation to change one to another configuration. So they are all linearly dependent. So therefore, the linearly independent one all come from here, because other one can be obtained from this one by this unity transformation. So like a choice basis. And but we only want to one set the basis. So this graph is like a one choice basis, and from this we can count how many independent states are there. And this graph just means a different choice basis. They are not independent states. Okay. So really from this, using this kind of thinking, we have this canonical string configuration. But the string can be 0 or 1. So here is that everything is 1, so we all have a string. And here the middle part is 0, so we have this configuration. So these two are legal configuration. Legal canonical configuration. Because the canonical one means that the first one we just draw all string all the way down, and all others joining this the first string. Just this canonical one. And we cannot draw other legal configuration. There's no other legal configuration. Because these two strings join, they either become 0 or 1. If it becomes 0, then this string has to join this string. If this string becomes 1, then these two strings can be 0 or 1. But this one has to be 1, because if this is 0, then this string have nothing to join. So this one has to be 1. So therefore, these two are only two possibilities. So the answer is that when you put the 4 and string on the sphere, we get 2 states. This is different from this loop. Remember, loop gas is that when you put the 4 and string on the sphere, you only get 1 state. There's no degeneracy. Here, put the 4 and string on the sphere, we get 2 states. Okay. And these 2 states actually is a kind of a topological degeneracy. Because the other, although I draw the string in this very particular way, but you should imagine far away from those points, the string can fluctuate according to their dancing rule, arbitrarily. And so this these 2 states are locally indistinguishable, because away from these 4 punctures, 4 and string, the string just fluctuates in the same way. They're locally indistinguishable. So therefore, these 2 states are really representing linearly degenerate states, and they are really qubits. So this really a topological qubits. By putting the 4 string and far away, we get near degeneracy. And this near degeneracy cannot be lifted by any other local perturbation. It means that when you're adding this coupled environment, degeneracy cannot be split. So therefore, their coherence cannot be destroyed by environmental noise. So this is a naturally topologically protected, maybe naturally fault tolerant qubits, because the degeneracy is topological. And so in some sense, the existence of this degeneracy can be said as a quantum memory. And this quantum memory is robust against environmental perturbation. So in this sense, we can say that the topological order is a quantum material with a quantum memory. We can say that way. So this is just an example of that. And then this is also a non-Abelian statistics. Because we have twofold degeneracy, when we exchanging two particles, two end of string, this twofold degenerate ground state may change among themselves, but this change will be 2 by 2 matrix rather than a pure phase factor. So actually, the end of string here will have a non-abelian statistics. Yeah. So I will end here today, and in the next lecture, we'll spend more time to discuss this model, and also we'll also develop more mathematical aspect of what I described today. Today I described cartoon picture, so tomorrow I will try to present some mathematical formulation of those cartoon picture. Okay.